Hi, my name is Margaret Troutner, and I'm going to tell you about our work on the theory of practice gap in operator learning. So first, I will explain what operator learning is so you can place our work in the broader context. So classical machine learning methods map between finite dimensional spaces. Think of some finite input vector and it's mapping to plus or minus one in some classification problem. But in science and engineering, we deal with partial differential equations, which involve infinite dimensional function spaces. So for instance, in this input and output of a Darcy flow PDE, we have our input coefficient is a function and our output, the solution of the PDE is also a function. So operator learning is a branch of machine learning that's naturally able to capture maps between infinite dimensional function spaces. And in computational mechanics, we can use neural operators to serve as surrogate models for complex physical phenomena. For instance, in a large multi-scale, potentially history-dependent system, one could use a neural operator as a surrogate model to capture some closure law, and then use this many times over the simulation of a system to help make it more computationally tractable. So I work a lot on the theory of operator learning, which I like to visualize in this iceberg here. So on the peak of the iceberg, we have universal approximation, which is a statement about model expressivity. You want to know that the model class you've chosen is expressive enough to capture your map of interest. If you go a little ways down the iceberg, we start thinking about error rates. So how large and wide your model needs to be in order to achieve a certain error. Similarly, we think about error rates in terms of the amount of data. How many data samples do we need to capture a certain error? And these error rates go like something like this. We say for n parameters, our error decreases like n to the minus alpha, or for n data samples, our error decreases like n to the minus beta. So the result I'm presenting today is somewhere in this frames of the iceberg dealing with error rates. I'm going to talk about a hardness result that actually relates these two kinds of rates, the parametric convergence rate and the sample convergence rate. So when I describe the theory to practice gap, on the theory side, we're thinking about model expressivity. So thinking about model size bounds, how many parameters you need to capture a certain low error. And in practice, we actually have to find these parameters. We have to identify them from a finite number of data samples. So this is a data efficiency question. And we're asking about a relationship between models with high model expressivity and models with high data efficiency. So to make this more explicit, on the parametric convergence rate on the theory side, we're saying that our error decreases like n to the minus alpha, where n is the number of parameters. And on the practice side, we're talking about sample convergence rates. So for n data samples, our error decreases like n to the minus beta. So higher alpha means better model expressivity, and higher beta means better data efficiency. And we're asking about the relationship between these two rates. So why would we even begin to think there's a relationship between these two rates? Consider polynomial reconstruction. To determine the coefficients of a degree little n polynomial, you need big N equals little n plus 1 samples. So in this case, the rates are actually the same. But for neural networks, there's a gap between these two rates. And this was first pointed out in this paper by Philip Gross and Felix Voigtlander. And what we do in our work is first, we improve on their rates for finite dimensional neural networks. And second, we extend the result to operator learning, to the infinite dimensional setting. So the finite dimensional result, again, we're talking about alpha as our parametric convergence rate, and beta is our sample convergence rate for approximation in LP. So expected LP error of our reconstruction with big N data samples converges at a rate n to the minus beta. So high beta means better data efficiency. And what we prove is that for approximation of functions from the d-dimensional unit cube to R with parametric convergence rate alpha, the sample convergence rate beta is upper bounded by 1 over p plus 1 over d times this correction factor that's always going to be less than 1. So basically, no matter how good your parametric convergence rate is, your sample convergence rate is limited. And this is in the finite dimensional setting. But if you look at this 1 over d factor and you think about operator learning in infinite dimensions, you think maybe we could push d to infinity. And that's exactly what we do, sort of, in the proof. The result in operator learning says that your sample convergence rate is upper bounded by 1 over p. In particular, for instance, suppose you're trying to do reconstruction and measure error in L infinity, you cannot expect to have any algebraic convergence rate in your sample error as you increase the number of samples, because beta is upper bounded by 0 here. So if you want to find out more about this hardness result, please attend my talk. Thank you.